Okay. So I will start sharing my screen. And class, if the connection is stopped or you cannot hear my voice, um, please inform me. You can inform me through the this Google Meet, or you can inform me directly through the WhatsApp group. Okay, because it happened in the past that I was disconnected. Okay, and then I keep on teaching for 20 minutes. And then the students inform me through the WhatsApp group that I already been disconnected for about 20 minutes. Okay. So I have to repeat again what I said for the past 20 minutes. So I hope that that won't happen again. And if I'm disconnected or you cannot hear my voice, you cannot see my screen, please inform me as soon as possible. Okay. And again, during my class session, you are most welcome to ask questions. You are most welcome to interrupt me anytime. Okay. If you don't understand, I can explain again. Okay. If you need me to explain further, to explain more about that specific topics, um, please ask. Okay. And I hope that I can give the best answer to you. Okay. So now I will share, and this is it. Okay. So can you see my screen?
Yes.
Kotak Google Meet ni pun boleh nampak eh? Can I get your response? Wait eh.
Boleh nampak.
Sekejap, macam mana nak hilangkan dia sekejap eh. Kalau saya pangkal dia. Sekejap. So I see that you can see this screen. Should I stop sharing? Stop sharing. Yeah. So maybe we can share this. I'll share one by one. Okay. So can you see my screen now? So
Yes, Doktor.
okay, so I'm sharing this. Sekejap. Apa lagi? Okay, so if you see from this, okay. So sekarang boleh nampak eh? Okay, can you see my screen? Sorry about that. Can I ask again?
Yes.
Okay, so this is the author. Okay, and before that, actually I want to show something else. Wait. So let me share my screen again. Sorry about that. I will share my screen and I will share this. Okay, so now you can see my screen clearly, right? So there's no Google Meet on the right side, right? Can I confirm that?
Yes.
Okay. So thank you for the confirmation. So now class, if you see from here, we are now in the week 12. Okay. So week 12, you should submit the progress report too regarding the transmitter prototype work. And the marks is about 2.5%. So we have extended the date until Saturday, 28th of December. Okay, so that you can have a suitable time to do the progress report. And you can follow the template from these instruction books, instructions manual. So there are a rubric, there is a marking form here and also the rubric, okay, including the progress report too. So in progress report 2, basically we want to see three things: timeline, number of meetings, and task completion. And these are the rubric how you will be evaluated. How much marks you will get is based on this progress report. Okay, this is the rubric. Okay, so if you need more time to do this report, you can inform me. I can extend the time for you, no problem. Okay. For me, I want you to write the best progress report, the best as you can. Okay. So this is about the project, and I hope that you can do as the best that you can. So I will start sharing my screen for the lecture notes. Okay. Okay, can you see my PowerPoint slide?
Yeah.
Okay, that's good. So last week we have stopped until this topic about the signaling rate, the bit rate, and also the bandwidth of PCM. Okay, so let me refresh again what we have learned last week. So sampling rate, also known as the sampling frequency that we have learned in the first part of chapter 4. Okay, the the sampling frequency, okay, which is based on the Nyquist theorem. Okay, so Nyquist theorem said that we should sample the signal with minimum rate of 2 times the highest input signal frequency. Okay, so Nyquist said that the minimum sampling rate would be 2 times the highest input frequency. Remember, if you have multiple input frequency, that means you have to choose the highest input frequency for the sampling rate. Okay, so in this example, you see that the sampling rate is calculated using a minimum Nyquist rate, 2 times FM. And you see that the unit here is sample per second, or known as in terms of hertz. Okay, so you can choose both. Either you want to choose a sample per second, or you can also write in terms of hertz. Okay, so sampling rate determines how many samples that we take in 1 second. Okay, so that determines the sampling rate. And then the next parameter is the bit rate. So bit rate is considered as the speed of transmission. How many bits are transmitted within 1 second? Okay, so it is a sampling rate multiplied with the number of bit per sample. Okay, so sampling rate is sampling rate, the unit is sample per second, and then you multiply with the number of bit used for each sample. Okay, and you will get a parameter in terms of bit per second. Okay, bit per second, or also known as the BPS. Okay, so one of the example is you can consider like the internet services at your home. For example, Unify. Okay, we have Unify 100, Unify 300, 500, and so on. So that numbers, okay, Unify 100, 300, 500, that one is determine the speed of transmission. Okay, the speed of transmission in terms of bit per second. Of course, if you go further, higher numbers of a bit rate, it requires a larger bandwidth to be allocated for you. So that's why you have to pay more for higher speed of internet services. Okay. Then we can see the bandwidth of PCM waveform. Okay. So PCM waveform, we can calculate the bandwidth based on the waveform of the pulse shift during the sampling process. Either we multiplied with the sync function in time domain during the sampling process, or we multiplied with the rectangular pulses during the sampling process. And both of these will give different in terms of bandwidth values. Okay, so the first one is bandwidth of binary encoded PCM waveform. So this is also known as the minimum bandwidth of PCM. Okay, so this is also known as the bit bandwidth minimum for PCM, which is equal or more than half of the bit rate. So for example, if the bit rate, okay, for example, if the bit rate is 10 megabit per second, okay, therefore your bandwidth gonna be half of it, okay, which is 1/2 times 10 Mbps. So you will get approximately 5 uh, mega, but the unit in terms of hertz, okay, 5 megahertz of bandwidth. So this minimum bandwidth is obtained when we use a sync function during the sampling process. However, normally, most of the time, we use a rectangular type of pulses during the sampling process where we're going to get a different value of bandwidth. So the next bandwidth is what we call as the bandwidth of PCM, which is equivalent to the bit rate. Okay. So again, this is if we use the rectangular type of pulse during the sampling process, and therefore we're going to produce the bandwidth equal to the bit rate. Okay. So in this case, if the bit rate, for example, is equal to 10 megabit per second, so therefore our bandwidth, the bandwidth of PCM, is equal to 10 mega, but the unit is in terms of hertz. Okay, so this is very important for your final exam. Make sure you know how to calculate the sampling rate, the bit rate, and also the bandwidth, which will be asked in the final exam for question number 3, okay, in the sub question. Okay, the calculation is easy. I believe you can score this calculation topic, no problem. Okay, so this part is very important for the final exam. Okay, so let's go to the example. An analog signal with a frequency of 40 kilohertz is sampling at is, sa- is sampled at sampling frequency equal to the minimum Nyquist rate. Okay, what does it mean? That means we sample equal to 2 times FM. Okay, each sample is encoded using 4 bit of PCM. That means n equal to 4. Okay, determine the bit rate. So we know that the bit rate from the previous slide, the bit rate is equal to the sampling rate multiplied with the number of bit per sample. Okay, so this is we have to find the sampling rate first. So SR is equal to 2 times the highest input frequency. So that means this is 2 times 40 kilohertz. Okay, so we will get 80 kilohertz of sampling rate. Then we multiply with uh, a number of bit. So the number of bit is bit rate is equal to sampling rate 80 kilohertz. You multiply it with the number of bit 4. Okay, so you get 320 kilobit per second. Okay, straightforward. Okay, so class, if you don't understand, please ask question. Otherwise, I will move to the next part. Okay, the next example. So the bit rate of a pulse code modulation is fixed at 63 kilobit per second. Calculate the bandwidth. So if you see that in this example, it doesn't mention which type of pulses used in the sampling process. Okay, so either we want to use a minimum bandwidth or we want to use a bandwidth of PCM. Okay, so normally, okay, normally if you read in other literature books as well, when they mention about the bit rate of PCM, we simply mention that the bit rate is equal to the data to the bandwidth. Okay, the bit rate of PCM. Okay, so this is only for PCM. The bit rate for PCM is equal to the bandwidth of PCM. Okay, so that means the bandwidth is equal to 63, but the unit is hertz. Okay, so this is the bandwidth of PCM. Okay, next example. This is also a good example. And for your information, we have asked this kind of question in the previous semester final exam. Okay, where you're gonna see that here we sample more than the minimum Nyquist rate. Okay, so in this example, an analog signal with frequency of 4 kilohertz. Okay, so this is input FM is sampled at frequency 10% higher than the minimum Nyquist sampling frequency. That means we will sample at 10% higher than the minimum Nyquist rate. Okay. So each sample is encoded with 3-bit PCM code before transmitted into the channel. Determine the bit rate. Okay. So the bit rate is equal to the sampling rate multiplied with the number of bit per sample. Okay. So first of all, we have to find the minimum Nyquist rate sample. Okay, minimum Nyquist rate. So Fs is equal to 2 times the highest input frequency. So that means 2 times 4 kilohertz. You get 8 kilohertz. Okay, so this is the minimum. But we sample at 10% higher. Okay, that means we have to sample so that means we have to sample, for example, Fs 10% higher. This is equal to Fs plus 10% higher than the minimum sampling rate. Okay, so 10% higher means the minimum sampling rate plus with 10% higher. Okay, so therefore we get 8 kilohertz multiplied with 0.1 times 8 kilohertz. Okay, so this is actually equal to 8 kilohertz. You plus with 0.1 of minimum sampling rate. Okay, so you will get around 8.8 kilohertz. Okay, so this is the sampling rate. Okay, then when we want to calculate the bit rate, so the bit rate is equal to the sampling rate, or the sampling rate multiplied with the number of bit, okay, per sample. So therefore 8.8 kilohertz, you multiply it with 3, so you will get the value 26.4 kilo bit per second as shown here. Okay, so this is 10%. If it is 20%, that means we have to add with 0.2 times the minimum sampling rate. Okay, so this the value 0.1 here is how many percent? Okay, remember this is 0.1 represented as 10%. Okay, if 20%, that means 0.2. Okay, 30%, 0.3, and so on. Okay, so that's how we calculate the bit rate if we want to sample more than the minimum Nyquist rate. Okay, and then what? The bandwidth of PCM waveform. Okay, so simply as bandwidth PCM. It doesn't specifically mention about the waveform and others. So the bandwidth of PCM, we understand that it is equal to the bit rate. Okay, so bandwidth of PCM is equal to the bit rate of PCM. Okay, which is equal to 26.4 kilohertz. Okay. Do you have question to ask regarding this example? Ada soalan nak tanya? So if there's no question, we can move to the next part, next topic about the baseband transmission. Okay. Okay. So if you see here, where are we now? Okay. Where are we now? So we are still in the transmitter part. Okay. We are in the transmitter part. Okay. So we have the input previously that we have seen that we have the input, for example, analog input or digital input. We can have any type of inputs, either analog or digital. And we have seen the formatting process in the transmitter. Remember the formatting process where we do the sampling process, we do the quantization process, and finally we do the encoding process. And we produce the PCM code word. Remember that we produce logic 1, logic 0, logic 1, logic 0, logic 1, logic 0, and so on. Okay. Now, the issue is how can we transmit this PCM code word 101010 into the medium? So now that's the issue. Okay. We have the code word, the logic numbers, but how can we transmit these logic numbers? So we have to convert it into the electrical pulses. Okay, so those numbers, logic 1, logic 0, needs to be converted into the electrical pulses so that we can transmit along the medium. But in this case, we want to use a baseband transmission. So baseband is a low frequency transmission where we usually use the same frequency as the input. And normally for the baseband transmission, we transmit along the wired medium. Okay, normally we transmit along the wired medium. So we convert the code word into electrical pulses. So how to do that? So we use a few methods that we call it as line coding. Okay, so the line coding consists of many types of coding techniques. Okay, among them is what we call as a non-return to zero and RZ. We also have the return to zero RZ, phase encoded, multi-level binary, and few others. Okay, so you only need to learn a few type of line coding only. Okay, not all the line coding. So you have to have the basic understanding about these line coding techniques. Okay, so if you see from here, okay, so we have the input. Okay, our input now is in the form of logic numbers. Okay, so now the input is logic numbers 101010. Okay, so we need to convert it into electrical pulses. Okay, if you see from here, we have two types of pulses. The first one is what we call as a PCM pulses. This is a unilevel pulses. That means we only have sorry, we call it as unipolar. Sorry, not unilevel, unipolar. Unipolar pulses. That means our pulses only have the same polarity, which is a positive polarity. Okay, so for example, this is a positive 5 volt, for example. Okay, so we only have positive voltage of pulses. Then we also have a bipolar pulses, which consists of positive voltage and negative voltage as the output. Okay, so this is what we call as a bipolar. We have positive polarity and negative polarity of voltage. Okay, and this is it. Okay, so we have asked this question before in the previous semester final exam. Okay, where the student uh, needs to determine the pulses at the output of the transmitter. Okay, given a certain input, determine the pulses. Okay, so let's go through this. Okay, so we can see from the left side. You can see from the left side. So the left side here we got contains of an RZ, unipolar, bipolar, RZ, AMI. And the input is this one. This is the input. Okay, so the input after the ADC, analog to digital converter. Okay, from ADC, remember from ADC, analog to digital converter, we produce 101010 logic numbers. Then we have to uh, put it into a system that convert it into the electrical pulses. Okay, so we have to produce the electrical pulses so that we can transmit along the medium. So how to do that? Okay, so let's go through one by one. So all of these we call it as a line coding. All of these we call it as a line coding, and there are many techniques in the line coding. If you see the first one on the left side, NRZL, non-return to zero level, L for level. Okay, so what happened into the non-return to zero level? Okay, so we have the input and what is the output of the source encoder. So this is actually a source encoder. Okay, we encode the source. Okay, so you see that the input, if the input is logic 1, we will produce positive output voltage. Okay, and you see that the terms here that we use is a non-return to zero. That means the output will not return to zero. Okay, and this is a bipolar output signal. Okay, so whenever we receive input logic 1, it will produce positive output voltage. And then input logic 0, it will produce negative output voltage, and then positive output voltage for logic 1, and then input logic 1, again positive output voltage. And then input logic 0, negative, 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 then positive output voltage, negative again, and positive. So whenever the input is logic 1, it will produce positive output voltage, and whenever the input is logic 0, it will produce negative output voltage. Okay, so let's go to the next one is non-return to 0, mark. M for mark. So that means this will, the output will have changes whenever the input is logic 1. Okay, whenever the input is logic 1, the output will change polarity. Okay, so let's go through this. Initially doesn't matter. Okay, initially doesn't matter. So in this example, initially it starts at 1. But for initial, you can also start at negative. No problem. Okay, that one is the initial state. We call it as the initial state. Okay, so in this example, the initial state is 1. Okay, sorry, the initial state is positive. Okay, positive. Then input logic 0, no change in the output. Then we receive input logic 1. Input logic 1, the output will change from positive to negative. Then another input logic 1, the output will change polarity from negative to positive. Okay. Then input logic 0, no change, no change, no change. Then input logic 1, change polarity from positive to negative. Then another logic 1, change to positive. Logic 0, no change. And logic 1, change polarity to negative. Okay, so that one is NRZM. So NRZM is based on the input logic 1. Whereas the next one, non-return to 0, S for space, where it will uh, change only if the input is logic 0. Uh, so now logic 0 will change the output. Okay, so if you see the initial state here, start at negative. Okay, then the next is input logic 0. Input logic 0 will produce changes at the output from negative polarity to positive. Okay, then input logic 1, no change, no change. Then input logic 0. Logic 0 will produce changes in polarity. Change polarity to negative. Another 0, change to positive. Another 0, change to negative. Okay. Then logic 1, no change. Logic 0, change to positive. Logic 1, no change. Okay. And then what? Unipolar, return to 0. That means single polarity, but always return to 0. Okay, return to 0 volt. Okay. So you see that for unipolar RZ, whenever the input is logic 1, it will produce positive output, then return to 0. Whenever the input is logic 0, it will maintain at 0 volt. Okay, it will maintain at 0 volt. So let's go through here. So the first one is logic 1. Okay, logic 1 will produce positive output voltage, then return to 0. Okay, so for the half of bit time. Okay, so maybe I haven't explained about the bit time. Wait, so the bit time here, if you see from here, the bit time is the time for 1 bit. Okay, so for 1 bit time for return to 0, okay, only half of the bit time will change. Okay, only half of the bit time it will change. Okay, so in this case, unipolar, if you see that for half of the bit time, it will be at positive, and then the other half, it will return to 0. Okay. Then the next input is logic 0. Logic 0, it will maintain at 0 volt. Then logic input logic 1 produce positive output for half of the bit time, then return to 0. Then logic 1 again, positive output, return to 0. Input logic 0 maintain at 0 volt. Logic 1 return, logic 1 return, 0 volt, then logic 1 input. Okay, so we have the unipolar RZ. Then we're going to see the bipolar. Okay, so bipolar return to 0. So bipolar, you're going to see that input logic 1 will produce positive output half cycle, half bit time, and then return to 0. Then if you have the input logic 0, it's going to produce negative output and then return to 0. Okay, so if you see from here, input logic 1 will produce positive output voltage, then return to 0. Then input logic 0 will produce negative output voltage, return to 0. Input logic 1, positive output, return to 0. Another one, positive, return to 0. Then we have input logic 0. So input logic 0, negative output, return to 0. Negative output, return to 0. Negative, return to 0. Then input logic 1, we produce positive output, return, positive output, return. Then input logic 0, negative output, return, and then positive return. Okay. And then what? The next one is RZ AMI. Okay. RZ AMI, return to 0, alternate mark inversion. Okay. That means, you see the word mark here. That means input logic 1 will change the polarity of the output. Okay. So if you see from here, so now it has an initial state. So initial state now, in this example, it starts with positive. For the first bit, initial, it produces a positive output and then return to 0. So this is only half of the bit time. Half of the bit time is positive, then return to 0. Then the input is logic 0. Okay. For input logic 0, no change. The output will remain at 0 volt. Okay, the output will remain at 0 volt. Then input logic 1. Input logic 1 will change the previous output polarity. Okay, the previous of input 1 polarity. Okay, previously the input logic 1 will produce positive. Now the next input logic 1 will produce negative output. Okay, and then return to 0. Okay, it will alternate. Previously is positive, now becomes negative. Then another input logic 1. So another input logic 1 will change the previous polarity. So from positive, it becomes the positive and then return to 0. Input logic 0, no change, remain at 0 volt. Then input logic 1. Input logic 1 will change the previous input logic 1 polarity. So previously is positive, now become negative, return to 0. And then change again for input logic 1, positive polarity, return to 0. Then input logic 0, no change at 0 volt. Then input logic 1 will alternate the previous. Previously is positive, now we get negative output and return to 0. Okay, so I think the left one is good for you to understand the concept of line coding, and on the right side you can read on your own. Okay, so there are many types of line coding. In the practical applications, there are many types. Okay, this only some of it. Okay, some of it are mentioned here, and there are many others. Okay, so the explanation is given here. Okay, the explanation of the line coding is given here. Okay, you can read on your own. Okay, now the next topic is digital modulation. Uh, so digital modulation, if you see from here, digital modulation in your lecture notes, it is referring to the transmission in the wireless medium. Okay, basically we have the digital data. We want to transmit the signal in high frequency, so we call it as a digital modulation. In order to achieve this, we have to modulate the input. Okay, we have to modulate the input code word into a wireless into the what we call the electromagnetic wave. Okay, maybe I can draw for you. I can draw for you. So where are we now? We are still in the transmitter side. Okay, so you see that again we can have any input, analog or digital input. Okay, then we process in the transmitter. Remember that we produce uh, 101010, right? And then now the issue is we want to transmit this signal into a high frequency output. That means we have to modulate these logic numbers with analog carrier. Okay, we have to modulate the logic this PCM code word with analog carrier. Okay, analog carrier, this is VC of T. Okay, so that we can produce, okay, we can produce an output. We can wait, so that we can produce an output with radio frequency output, a high frequency output, which is capable to be transmitted in the medium, okay, in a wireless medium. Okay, so basically we want to transmit as analog. Okay, we have the digital code word. Okay, we have the PCM code word. We have to convert this into the analog waveform. This analog waveform is electromagnetic wave. Okay, electromagnetic wave is analog. Okay, electromagnetic wave is analog. So in order to do that, we have to modulate the PCM code word with analog carrier. Okay, so what we get is actually uh, similar with what we have learned in chapter 3. Okay, so when we modulate with carrier, okay, when we do modulation with the carrier, the characteristic of the carrier will change. You have learned that in chapter 3. Okay, so what are the characteristic of carrier that will change? There are three, right? The first one is amplitude. Okay, if the input change the amplitude of the carrier, we call it as ASK, amplitude shift keying. Okay, and if the input change the frequency of the carrier, we call it as FSK. frequency shift keying. And if the input change the phase of the carrier, we're going to produce PSK, phase shift keying. Okay, phase shift key, where you're going to learn this in the lab as well, later in a lab session. In the lab session, in another lab session subject, you will learn about this. I'm not sure, maybe lab 3 if I'm not mistaken. So now you are going to learn about the fundamental, the theoretical concept. Okay. So this is the basic block diagram for digital modulation. Okay. So we have this input data. Okay. We put it in the precoder. Then we send to the modulator, where in the modulator, we modulate with analog carrier. Okay. So the precoder basically will produce the uh, logic 101010. Okay. Then we put inside the modulator, okay, where it will modulate with the analog carrier. Okay. And of course, you will produce an analog output. Okay. You will produce an analog output. So the band pass filter will remove the unwanted frequency signal. Okay. And we amplify the signal. Okay. To make it bigger. Okay. To make it bigger, so that we can transmit along the medium. Okay. In the medium, we have the noise. Okay. And of course, when we receive the signal, gonna be a bit weaker than the transmitted signal, and it contains a lot of noise. Okay. So we have to use band pass filter to remove the unwanted frequency, which is the noise, and we should amplify the signal so that we can do the next process. Okay. So in the demodulator, we put inside the demodulator, and then we decode the signal and produce the output. Okay, so this is another process, the band pass filter, and then the carrier and clock recovery, so that we can have the output in terms of logic 1010 at the output. Okay. So the next part is the energy bit over noise density. Okay. Energy bit is EB. Okay. Um, so EB, the bit energy, is equal to the received power. Okay, received power times the times the T here is the bit. This is a bit time, bit duration. TB is a bit duration. So power in terms of watt, if you multiply with the time in second, so it becomes watt second. Watt second, or known as the joule. Okay, watt second is joule. Then we have another parameter, N0 is equal to the thermal noise power density. Okay, thermal noise power density. This is equal to K Boltzmann constant multiplied with the noise temperature. Okay, in Kelvin. Okay, so this will also produce joule. Okay, so EB over N0, okay, is a parameter in the digital system where it is actually equivalent, okay, to the signal to noise ratio in analog. Okay, in analog, normally we try to find the SNR, right? In digital system, we normally try to find the EB over N0. Okay, so this is not covered in detail in this subject. Okay, this topic is not covered in detail in this subject. it will be covered in details for another subject, the digital communication subject. Okay. So channel capacity is equal to the maximum bit rate. Okay, so this is actually equal to the bit rate maximum. Okay, maximum bit rate. The maximum bit rate that can be decoded by the receiver. Okay, so that means the transmitter needs to know how much will be the channel capacity so that the receiver able to receive the signal and decode the signal. If the transmitter transmit more than the channel capacity, the receiver will not be able to decode the signal into original signal. Okay, so that's why the transmitter and receiver must be synchronized. Okay, so the channel capacity is equal to 2 times bandwidth log 2 of M. Okay, so assume no noise is present and NRZ encoding. So the minimum necessary to pass the M array digitally modulated carrier, the bandwidth is equal to 2 times K. Okay, what is K? K is equal to log M, log base 2 of M. So K is actually the number of bit. Okay, so previously we used the terms N, right? Previously we used the terms N. So now it uses the terms K. So don't be confused. K and N in this example is the same, the number of bit. Okay, M is the symbol, the number of symbol. Okay, for example, if we use the number of bit equal to 2, okay, we're gonna have M equal to 2 power of 2, which is equal to 4. Okay, so you see that M is equal to K power of 2 power of K. So maybe I should explain here. Yeah, M is equal to 2 power of K, okay, which is 2 power of 2. So we're going to get 4 symbol. This is similar like the one that we have learned previously. So what is the 4 symbol in this example, in my example? Okay, so if you use 2 bit, that means I'm going to have 4 symbol possibility starting from 0, 0, 0, 1, 1, 0, 1, 1. Okay, if I use K equal to 3, for example, okay, if I use K equal to 3, that means M is equal to 2 power of 3, which is equal to 8. So I'm going to have 8 symbol. So what are the 8 symbol? The symbols are from 0, 0, 0, 1, 1, 0, 1, 1. Oh, sorry. Okay. If I use 3 bit, that means I'm going to have 8 symbols starting from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So I have 8 symbols. Okay. So M representing the number of symbol. Okay, the number of transmitted symbol. Okay, and you see that the symbol is depending on the number of bit. Okay, and if you see from here, this bandwidth is equal to okay, so you have to correct this one. This is supposed to be not 2 times K. This is supposed to be 2 power of K. So class, please correct your notes. This is supposed to be 2 power of K. Okay, 2 power of K, not 2K. So don't be confused. So this is supposed to be 2 power of K, where this is actually uh, log base 12. Okay. Oh, sorry. Wait, itulah 2K. Sorry about that. Okay, so this is the bandwidth. Sorry about my mistake. So the bandwidth is actually equal to the capacity divided with 2 times the number of bit. Okay, so this is correct. Okay, so the capacity in terms of bit per second, you divide with 2 times K. Okay, 2 times number of bit. So that means this is the bandwidth of the signal. Okay, the bandwidth of the signal. Capacity would be the maximum bit rate. Okay, capacity would be the bit rate maximum. Okay, and then what? So we have seen about bit rate. So the bit rate is the speed of transmission measured in terms of how many bit you have transmitted in 1 second. So that's why the unit is bit per second. But we also have another parameter, what we call as a baud or symbol rate. Okay, so baud or symbol rate determines how many symbol that you can transmit in 1 second. Okay, what is a symbol? Symbol is this one, the one that I've shown before. For example, 000, 001. All of these are symbols. Okay, all of these are symbols. So now the issue is how many symbols I can transmit in 1 second. Okay, so this is equal to C divided with the number of bit. The capacity bit per second divided with the number of bit used to encode the signal. The unit is baud. Okay, how many baud? Or we can also write symbol per second. So either you use symbol per second or baud. Okay, in practical cases, normally we call it as baud. Okay, or normally it mentioned about the baud rate. How many baud rate, for example? So it determines how many symbol that you can transmit in 1 second. Okay, so let's go through the example. Okay, given the binary bit transmitted in the form of 0 volt for bit 0 and 1 volt for bit 1 at t equal to 0.1 microsecond. Calculate the baud and bit rate. So the symbol rate, the baud rate or the symbol rate R is equal to 1 over T. Okay, 1 over T means that 1 over 1 divided with 0.1 microsecond. So you're going to get 10,000 symbol per second or baud. Okay, so if you see from here, so this is not mentioned about 1 over T. It's not mentioned 1 over T over here. But here it's mentioned that the baud rate or the symbol rate, okay, okay, you see that the given the binary bit. So now we have the binary bit, okay, the binary bits. So now our symbol, that means we are using 1 bit actually. Okay, we are using 1 bit. That means 2 power of 1. So we're gonna get 2. So this is either logic 0 or logic 1. Okay, that means one symbol is 1 bit. Okay, in this example, one symbol is 1 bit. Okay, in this example, so that's why the word here is binary bit. Okay, so the keyword that you can see from here is binary. Binary means that either logic 1 or logic 0 for symbol. Okay, that means your symbol either logic 1 or logic 0. In this case, we are using 1 bit. Okay, so either symbol, this symbol, or another symbol. Okay, so that's why given the time for each uh, bit or symbol, okay, in this case 1 bit is 1 symbol, so you divide with the time, so you're gonna get the in terms of symbol per second. Okay, so 1 divide with the time taken for 1 bit or 1 symbol in this example, so you're gonna get symbol per second or baud. Okay, remember in this example is binary, that means 1 bit 1 symbol. Okay, so that's why you can divide with the bit time. Okay, and you're gonna get symbol per second. Okay, and then what? Find the bit rate. Actually, the next question, find the bit rate. So in order to do that, we need to find the number of symbol. The number of symbol in this example is actually 2 power of 1. Okay, where k is actually equal to 1. In this example, because it mentioned about binary, k equal to 1. Okay, so that's why we get to symbol either logic 1 uh, for either logic 0 or logic 1. So therefore, the number of bit per symbol, okay, k is 1 bit per symbol, as I mentioned. Okay, it is n, k or n log base 2 of m. So log base 2 of 2 is equal to 1 bit per symbol. Okay, because we have 2 symbols, either logic 1 or logic 0. Okay, our symbol only 2 possibility, 0 or 1. Okay, so that means our symbol is 2 and number of bit is equal to 1 bit. Then the bit rate is equal to the number of bit times the bit rate. Number of bit is equal to 1. We multiplied with 10,000. Okay, 10,000 is where? From this 10,000 symbol per second. Okay, so we get this 10,000 bit per second. Okay, and then what? The next question, given the minimum Nyquist channel capacity to transmit binary bits in 4 symbols, 00000011011 is 2000 bit per second. Okay, so this is the bit rate, bit per second. Calculate the minimum bandwidth for each symbol and the baud rate. Okay, so if you see from here, the Nyquist channel capacity is given. Okay, Nyquist channel capacity, that means the maximum bit rate, is given in the question as 2000 bit per second. Okay, and how many symbol? Also given in the question. Okay, we have 4 symbol, 00, 01, 10, 11. That means we have 4 symbol. Okay, 4 symbol, which is equal to m. Okay, the number of bit per symbol is actually equal to log base 2 of m. So log base 2 of 4, we're going to get 2 bit per symbol. Okay, 2 bit per symbol. Then the minimum bandwidth for each symbol is equal to bandwidth. The minimum bandwidth for each symbol is equal to bandwidth B divided with 2K. Okay, what is this actually? So B is a channel capacity. You divide with 2 times the number of bit. Okay, So that means this is 2000, okay, 2000 bit per second. You divide with 2 times the number of bit is 2. Number of bit per symbol is 2. So times 4, so we get 500. We get 500 500 hertz. Okay, 500 hertz. If you divide, so you get 500. Okay, and then what? The baud or symbol rate is equal to baud per symbol rate. R is equal, calculate the baud rate. Symbol by baud or symbol rate. R. Okay, so symbol rate is equal to why see symbol and the baud rate. Find calculate symbol baud rate. Baud or symbol rate R is equal to 1000. So symbol rate here is the number of bit times. So this is actually the number of bit or K you multiplied with the number of here is minimum bandwidth. This is actually you multiplied with 500. Yeah, this is hertz. So this is 1000. So I will check again about this matter. Why suddenly 200? Wait, okay. This one is baud or symbol rate. Symbol rate. Yes. And the number of bit per symbol is 2 bit per symbol. And then the minimum bandwidth for each symbol is 500 hertz. Okay. Baud rate 1000. Baud rate is supposed to be 2000 divided with 2. Okay. So this is actually the minimum channel capacity. Number 7. I will check again about this part. I will check again about that. Okay. Then this one is so if you say from here the baud is C over K. Okay, if you use this one, I think this one we use this baud. Baud is capacity divided with K. So yeah, so this is actually C divided with K. So the channel capacity that we calculate previously is 2000. Okay, so 2000. So this is a bit per second. You divide with the number of bit that we use for each symbol is 2. Okay, so we get this is 1000. Okay, 1000, but the unit should be symbol per second. So this is not supposed not to be BPS. This is actually 1000 baud, or you can also write in terms of symbol per second. Okay, it should not be R over here. This is This is, don't be confused, class. This R is actually the baud rate, the baud or symbol rate. Okay. Uh, so I'm confused about that. So we normally use R. In the previous slide, R is for the data rate. Okay. So for the baud rate or symbol rate, it is equal to capacity divided with the number of bit used in this example. Okay. Okay. Next part. Class, can I get your response? Are you still there? Can you hear my voice? Can you see my screen?
Yes.
Okay. Okay. So I go to the next part. Amplitude shift keying. Okay. Amplitude shift keying. So amplitude shift keying is a modulation process of uh, digital code word with analog carrier. Okay, digital code word and also the analog carrier, where it will change the amplitude characteristic of the carrier. Okay, so the carrier signal is given here, Vc cos omega t plus theta, and the general equation for ASK is given here, 1 plus Vmt multiplied with Vc cos omega ct. Okay, so this VMT is the input. Okay, our input is either logic 0 or logic 1. Okay, whereas for the carrier, this is the analog carrier. Okay, so now we have to see the difference of input. Okay, our input is only two possibility, either logic 0 or logic 1. Okay, so if you see from here, if the input is logic 1, okay, if the input is logic 1, VMT will be equal to positive 1. Okay, if the input is logic 0, the output gonna be negative 1. Okay, so that means if you use this one logic number, I can say that this is the output. If we have logic 1 and logic 0. Logic 1 will produce positive output. Logic 0 will produce a negative output. Okay. So if you see the first one for logic 1, logic 1 means that it's going to produce positive 1. That means 1 plus 1. Multiply with the carrier. So you're going to get 2 Vc cos omega ct. Okay. Then input logic 0. For logic 0, we produce negative output, negative 1. That means 1, this is actually 1 plus negative 1. So that means 1 minus 1. Okay, times Vc cos omega ctt. Okay, omega ct. So you're going to get 0 multiplied with anything will produce 0. Okay, so logic 1 will produce output. Logic 0 will produce 0 output. Okay. And this is how the signal looks like. Okay. So our input is logic 1, logic 0, logic 1, logic 0. And the output is this one. Whenever the input is logic 1, we have the 2 times VC cos omega CT at the output. Whenever the input is logic 0, it will produce 0 output. Then input logic 1, we produce another signal, then 0. So this looks like on and off signal. Okay, this looks like an on, off, on, off, on, off signal. So ASK is also known as the OOK, on, off key. Okay, the other name, on, off key. So in this case, you see that the baud rate and the bit rate is the same. Okay, because the number of bit used for binary is 1 bit. Okay, so you see that the output, this is the output signal. We have the input and we have the output. Okay, 101010 produce signal, no signal, signal, no signal, signal, no signal. Okay, then in terms of frequency domain, okay, the first one we have the input. For example, if you have the input up to 3 spectrum like this, 3 different frequencies from FM until 5 FM. So what about the bandwidth? The bandwidth of the output is equal to 2 times FM. Okay, 2 times NFM actually. 2 times NFM. Okay, so for the first fundamental, N is equal to 1. Then the third harmonic, we're going to produce 2 times 3. So it is 6 FM. Okay. N is the number of harmonic. Okay, the number of harmonics. Fifth harmonics, 2 times 5. So that means 10. Okay, 10 FM. Okay. Okay, the next, this is also, this picture shows the process of modulation process, ASK, or known as the OOK. So input here, we have the input logic 1, logic 0, logic 1, logic 1, logic 0, logic 0, logic 1. You put inside the multiplier, and we also inject with the VCT. Okay, and the output will produce signal for input logic 1, no signal, input logic 0. Input logic 1 will produce output signal, okay, and then 0, 0, no signal, and then another input logic 1 with signal output. Okay, so it looks like on off signal. Okay, so this picture happens at the transmitter. Okay, this is a transmitter. Okay, then in the receiver, so this is at the receiver side. Okay, so in the receiver, we have the OOK signal or ASK signal. So we put inside the multiplier. Then we have the carrier recovery circuit to produce the carrier signal, the same frequency of the carrier signal. Okay, we inject to the multiplier. So this is VCT. Okay, we use the same carrier frequency, carrier frequency to produce the output. Okay, so remember when we multiply 2 signal, actually we're going to produce at least 2 sideband, right? The upper and lower sideband. Okay. Then we put inside the low pass filter to select only the low frequency signal. Okay, select only the low frequency signal at the output. Okay, so we produce the output. So this is a coherent detection. Why? Because we use the carrier. We use the carrier. We use the carrier signal for the demodulation process. Okay, so that's why the name is coherent. Okay, another terms is non-coherent. Non-coherent, we are not using the carrier signal to recover the original signal at the output of the receiver. Okay, so in this case, since we use the carrier properties, we inject with the carrier, so this is named as coherent. Okay, so demodulation OK can also have done using the envelope detector, non-coherent or non-synchronous. So this is without the carrier signal. Okay, and this is the probability of bit error. Okay, probability of error. Okay, probability of error. What does it means by probability of error? The probability of the bit that we send will be in error. Okay, so this is PB. Okay, so P, probability of bit error. Okay, probability of bit error is equal. This is for optimum. This is for coherent. So this is for ASK, coherent detection. So what is the error? What does it mean by error? So I repeat again, the terms error here means that if the transmitter transmit a signal of logic 101010, for example, from transmitter, okay, suddenly the receiver interpret the signal as 1111010. Now, so sorry, 111. So, yeah. 111010, for example. Okay. So you see that this is the error. It's supposed to be logic 0, but the receiver interpreted as logic 1. Okay, this is an example of error. So now, what is the probability that this error will happen? So that's why we calculate using this equation. Okay, what is the probability that this error will happen? Okay, so the probability of bit error for ASK, optimum, for the ASK coherent detection, it is equal to 1 over 2 ERFC square root of EB over 2N0. So I suggest you to make a big bracket like this. Okay, because the square root of EB over 2N0 is belong to the ERFC function. ERFC is a function, also known as a complementary error function. Okay, ERFC is a complementary error function. It's a function, you know. So ERFC of Z is equal to 1 minus ERF of Z. ERF is the error function. So we have ERFC, we also have ERF. Okay, ERFC is a complementary error function, whereas ERF is the error function. Okay, and it is shown in this table. Okay, it is shown in this table. Okay, so if you see, the first table is about ERF table, and the second table is the complementary error function table. How to read the table? So I will show you, class. So the first one is this is ERF. So this is ERF of X. Okay, X is the input. Okay, so X can be from 0 until 3.2 something. So the first row here is for x 0.0. Okay, you see that we have 0.0 over here, then we have 0, 1, 2, 3, 4, 5 until 9. Okay, so for x equal to 0.00, okay, the ERF would be this one, 0.0000. Okay, and for x equal to 0.09, okay, x equal to 0.09, the output would be 0.10128. Okay, and I repeat again for another example. Let's say over here, okay, 0.4. So this is 0.41, 0.42, 43, 40, 41, 42, 0.43, 0.44, 0.45 until 0.49. Okay, if x is equal to 0.40, that means the ERF 0.40 is equal to 0.42839. If the input is x equal to 0.49, for example, then ERF of 0.49 would be equal to this one, 0.51167. Similar with another example. If you want to see another example, if you see from, for example, this one, if let's say the input is x equal to 0.21, for example, then ERF 0.21 is equal to 0.99552. 552. Okay, so you have to know how to read the table for the final exam later. Okay, so we have to understand first, if the x is certain value, then what is the output of ERF? Okay, and this is the first table. For the second table, similar how we read the second table, you see that this is ERFC. Okay, so for x equal to x equal to 0.00, ERFC function is equal to 1.000. Okay, 1.00000. Okay, and then for example, x equal to 0.40, for example, ERFC is equal to, sorry, so this is, sorry, yeah. Okay, yeah. So let me do corrections. This is ERFC 0.00. So you will get 1.0000. Okay. ERFC for x 0.40, that means ERFC 0.40. So you will get over here 0.57161. Okay. So in the previous slide, it shows that this one, ERFC equal to 1 minus ERFZ. Okay, so let me show you about this one. So ERFC, for example, of 0.40, this is equal to 1 minus ERF 0.40. So if you see from here, this is 1 minus, if I go back to the first uh, table, okay, error function table, I get 0.42839. Okay, So 0.42839. And I will get the same value, 0.57161. Okay, 57161. Okay, is it 43289? Okay, 839, and this is 83. Okay, this one, 0.42839. So I will get the same answer actually. Okay. So in the final exam later, you will be asked to find the using the ERF table. Okay. Okay. So this is how we read the table. So let's go for the example so that we can have more understanding. Okay. Given EB over N0 is equal to 0.32, find the probability of error if we use ASK coherent detection. So we use this equation 1 over 2 ERF big bracket, okay, square root of EB over 2 N0. So this is equal to 1 over 2 ERFC in bracket square root of 1 over 2 EB over N0. So this is just to the arrangement. We put out the 1 over 2 so that we can collect the EB over N0 over here. Then we can put inside the value. Okay, so 1 over 2 ERFC, this is a big bracket, square root of 0.32. So 0.32 is actually from the question. Okay, so we get 1 over 2 ERFC 0.16. This is bracket. Okay, so we get this value. Okay, so when you get this value, either you want to choose a first table or the second table. My advice is to choose the second table would be better. Okay, the second table, if you see that we already get the value 0.57161, which is over here in the table. Okay, 0.4 and 40. Okay, so 0.571161. Okay, and it's given here in the it is given here. Okay, so this also wants to show you if we use a first table. So if we use it from the first table, okay, the first table. So we use 1 minus ERF, error function 0.4. From the first table, we find here. Okay, this is the first table, error function table. So we get this. How do we get this? Okay, the first table, if you see over here, okay, the first table, okay, 0.40, we get 0.42839. Okay, so 0.42839. So if you minus, you will get this answer. So if you want to use the second table, will be better. You can directly get this value. Okay, so this value you can directly get from the second table. Okay, second table also will produce a straightforward answer. Okay, so therefore, once you get this, you can put into the equation. Okay, so ERFC 0.4 is equal to 0.57161. Remember, we have to multiply with 1 over 2. then we get 0.2858. Okay. So in this case, the probability of error would be 0.2858. Okay. And this is for non-coherent detection. So maybe I should go back for a while. Okay, I go back. Sorry, class. So the bit error, I go back to this slide. This is for coherent detection of ASK. So if you might wonder, where does this error happen? Okay, so where are we now? So we are actually at the receiver side. Okay, class. We are at the receiver side now. Okay, so the issue now is how much will be the probability of bit error at the receiver if we use a ASK and coherent detection at the receiver. Okay, so the probability of error is depending on the type of modulator that we use in the receiver. For coherent, that means we need the carrier signal inject to the receiver so that we can do the demodulation process. Okay. And what about if we use a non-coherent? So that's why we have to go back, fast forward. What about non-coherent? Non-coherent means that we are not using the carrier properties. So non-coherent, we are not using the carrier signal, okay, to do the demodulation process at the receiver. Okay, so the equation would be straightforward. 1 over 2 exponent in bracket negative EB over 2N0. So this is ASK, non-coherent detection. Again, class, we are at the receiver side. Okay, we are now at the receiver. Okay, we receive the signal ASK and we use a non-coherent. How much will be the PBE? Okay, so the probability of bit error is equal to E power of negative EB over 2N0. So example, given EB over N0 is 1.11. So you put inside this value into the equation. So class, if you see from here, we don't need to use table anymore. We can straightforward using our calculator. So I suggest you open your calculator and try it. Okay. So you see that 1 over 2 E exponent power of EB over, negative EB over 2N0. So we rearrange the equations, okay, like this. And we put inside the value. Okay, so 1.11 is actually EB over N0. You multiply it with negative 1 over 2, so you produce negative 0.555. Use your calculator, okay? So for my calculator, okay, the way I do it is by shift ln. Using my calculator, I use the shift ln, okay? So this is, if you see from your calculator, find the symbol E power of X. Okay, find the symbol E power of X in your calculator. Then you can write negative 0.555. Okay, so you will get 0.5741 from your calculator. Okay, from your calculator. Okay, this is from calculator. Okay, you multiplied with 1 over 2, then you get 0.2870. Okay, 0.2870. Straightforward, using your calculator. Okay. And then what? The next part would be the FSK. Okay. So we have finished learning about the amplitude shift keying. Now we move to the frequency shift key. So frequency shift keying means that the modulation process will change the frequency property of the carrier. Okay. So now we go back to the transmitter side. Okay, we go back to the transmitter side. We have the input and we inject with the carrier, analog carrier. Okay, in order to produce analog output in the form of electromagnetic wave. Okay, so the input is in terms of logic 1, logic 0, logic 1, logic 0, 1, 0. And we want to produce an output FSK. Okay, so the general equation for VFSK is given as VC cos 2 pi FC plus VMT delta F. Okay, so delta F is a peak shift in the carrier frequency, which is proportional to the amplitude of the binary. So the term that will change is actually the VMT. The VMT, as the previous, okay, would be equal to positive 1 if the input is logic 1. Okay, if the input is logic 1, VMT will produce positive 1. Okay, if the input is logic 0, VMT will produce negative 1. Okay, so this is for logic 0 input. Okay, so let's go through for input logic 1. Okay, VMT would be equal to positive 1. That means your equation would become VC cos 2 pi FC plus VMT delta T. So this is supposed to be, this can cancel this one actually. So this is actually positive 1. You don't need to write VMT again, okay? So this is actually FC plus delta F. So this is actually FC plus delta F. Okay, for input logic 1. For input logic 0, VMT will be equal to negative 1. Okay, that means it's going to be VC cos 2 pi FC minus 1. So this is supposed to be minus 1 delta F. Okay, so you can correct your notes. So this is supposed to be FC minus delta F. Okay, so class, you see from here, the changes would be in terms of carrier frequency. Okay, so that means the carrier frequency will move from, this is the rest, and then FC plus delta F for the maximum frequency, and FC also move from FC until FC minus delta F. Okay, so the frequency changes. Okay, so the bit rate or the baud rate is equal, but the bandwidth can be approximated by Carson's rule. So you might wonder why the bit rate and the baud rate is equal. Because we are using binary input. Okay, class? It is equal because we use a binary input. Our input is only either logic 1 or logic 0. That means we are using 1 bit. Okay, K equal to 1 bit. Okay, so that means the number of symbol M is equal to 2 power of K. That means 2 power of 1. So we get 2 symbol where this is logic 0 and logic 1. Okay, this is the most basic. Okay, so the bandwidth using Carson's equal to 2 times delta F plus B, where B here is the input frequency. Okay, FM, the highest input frequency. Okay, so this is in the transmitter side. Okay, in the transmitter side, for the modulation process, you see that we have the input here, the picture above, picture A. Our input is logic 1, logic 0, logic 1. We put inside the multiplier over here, and we also put inside the inverter. So the inverter will inverse the input. It will become 0, 1, 0. Okay. From 1, 0, 1, we inverse the bit. 1 in logic 1 become logic 0, logic 0 become logic 1, logic 1 becomes logic 0. Then put inside the second multiplier. So each multiplier we put the oscillator frequency F1 and also the F2. Okay. In this example, F1 is larger than F2 in this example. Okay. So the output gonna be so this is like a ASK output. When you multiply, you're gonna get for input logic 1, we have signal. Okay, we have the signal. Then input logic 0, no signal. Input logic 1, we have the output signal. Okay. Similar with the wave for the second multiplier. Okay. So since second multiplier has a low frequency in this example, how do I know that? Based on the graph given over here. Okay. So you see that input logic 0 will produce 0 output, and then input logic 1 will produce an output signal which has a low frequency. Why low frequency? Because the number of ripples is small compared to the number of ripple above. That means if the ripple is very close one to another, that one is a high frequency. Okay, so this is for input logic 1. Then input logic 0, no signal. Okay, so for this one, we put inside the adder over here. Adder will combine the signal, okay, to become like this. So you have for input logic 1, okay, that means we base from the original input. Input logic 1 will produce an output with high frequency. Then input logic 0 will produce output with low frequency. Low frequency. Then input logic 1, okay, from here, the original, okay, will produce, input logic 1 will produce high frequency output. Okay, so that means for FSK, input logic 0 will produce low frequency output. Input logic 1 will produce high frequency output. So the output will looks like high frequency, low frequency, high frequency, low frequency. Okay, that's how the FSK looks like. Okay, similar with picture B. So this is on shown here. Frequency modulated oscillator produced the same kind of output. And this is it. Okay, so this is the waveform of FSK. And this is important for you. So this is a binary FSK. Binary FSK. Okay, so this is a binary FSK, which is also known as BFSK. Okay, The way we write in digital communication, the way we write is using the memory. So for your information, the way we write uh, about ASK, FSK, PSK, we write in terms of memory. So this one is actually for FSK. Normally we write it M FSK, where the M is based on the number of symbol. Okay. So for example, uh for bit for single bit for bit k equal to 1, okay, for k equal to 1, m equal to 2 power of 1, so we get 2. Okay, so that means we can write it as 2 fsk. So that means I can write it like this: 2 fsk is equal to the binary fsk. Okay, we also have another type of FSK. Remember, we have FSK, ASK, and PSK has many family members. Okay, I can say that like a family members. So the first one is it depends on the value of number of bit and the symbol. And I give you another example. If k equal to 2, for example, we have m equal to 2 power of 2, we get 4. That means we're going to produce 4 FSK. Okay, and so on. So k can be from 1 until 8. Okay, k normally from 1 until 8. Normally, from 1 until 8. Okay, so if you see 8 to power of 8, you're going to get 256 symbol. Okay, 256 symbol. Similar with ASK, class, similar with ASK, we also write in terms of MASK. MASK. Similar with PSK, MPSK. The way we write the way we write the symbol, okay, the way we write the terms of the symbol, MASK, MPSK. Okay, for binary, for if I use a single bit, it can be a binary ASK, BESK. Okay, and for PSK, if I use a single bit, okay, this is k equal to 1, it can be BESK, and so on. This is just a terms. BPSK is just a terms. BASK also a terms. Okay, BFSK also a terms to show the binary. Okay, so let's go back to this this waveform. So you have the input logic 0, logic 1. So this is the input. Okay, input logic 0, logic 1, 0, 1, 0, and so on. So remember, as the previous one, you see that logic 1 high frequency, input logic 0 low frequency. Okay, so the first one is logic 0. So we're going to produce a low frequency output. We call it as Fs, where this is a space frequency. Okay, space frequency. And the next one is logic 1. Input, going to produce high frequency output. We call it as Fm. Don't be confused. This is not the input. This is what we call as a mark frequency. Okay. Then input logic 0, we're going to produce low frequency output, space frequency. Okay. And then logic 1, mark frequency, space frequency, and so on. So you see that the output, okay, you see that the output, uh, in this case, the output is high frequency, low frequency, high frequency, low frequency. Okay, so this is important for the final exam, where you will be asked to describe about the binary phase shift keying. Okay, the binary phase shift keying, we are using 1 bit and we produce 2 symbol. The symbol is either logic 0 or logic 1. Okay, the symbol is logic 0 or logic 1. Okay, there are two possibility of symbol only. So this is binary phase shift keying. Okay, BFSK. Okay, and you can also explain by drawing this figure, okay, in the final exam later. So this can be used to answer the final exam question. Okay, the question asks you to explain, okay, to describe the binary phase shift key. So among the possible answer is to draw this signal. Okay, you can draw this signal. Okay, simple, right? Remember, input logic 0 produce a low frequency output, input logic 1 high frequency output. So this is very important for the final exam. Okay, and if you see from here, this is the input and this is the waveform. Okay, high frequency, low frequency, high frequency, low frequency. We have seen this. And what about the bandwidth of the spectrum? Okay, imagine if you have up to fifth harmonic of input. Okay, this is the input. So the output gonna be 2 times n fm plus delta f. This is according to the Carson's bandwidth. Okay, for the fundamental frequency, the bandwidth gonna be 2 fm plus 2 delta f. For the third harmonic, 2 times 3 fm plus delta f. 2 times, for the fifth harmonic, 2 times 5 fm plus delta f. Okay, so this is how we calculate the bandwidth of FSK. Okay, so let's do a simple example. Okay, determine the bandwidth for the FSK modulated signal when the oscillator 1 fits 270 kilohertz and oscillator 2 fits 100 kilohertz. So we have a this one, that means this is F1, this is F2. Okay, what does it mean? So this is actually referring to this picture. Okay, referring to this picture. Okay, so we have two frequency and the baud rate is 1000 bit per second. Okay, determine the bandwidth. Okay, so in this case, the baud rate is equal to the bandwidth. Okay, the baud rate is equal to the bandwidth as given over here. Frequency, space frequency. Yeah, this statement, the bit rate and the baud rate of binary FSK is equal. Okay, this is only for BFSK. Plus, this is only true for BFSK, binary phase shift key. Okay, where the baud rate equal to the baseband, the bandwidth. Okay, which is R equal to 10 kilohertz. Okay, so baseband bandwidth so this is actually from here. So the baud rate equal to the bit rate and equal to the bandwidth in this example. So this is also equal to the data rate, the bit rate as well. Okay. So baud rate equal to bit rate equal to the bandwidth. This example. Sorry. So this is confusing. And so class, please correct your notes. This is the you see the yeah, the bandwidth can be approximated by B, where FM is replaced with B. So the bit rate representing the input, the input FM. So if you see from here, this is the bit rate. Okay, so the bit rate okay, so the baud rate is equal to the bit rate. Okay, in this case where this is referring to the bandwidth. So this the terms is quite confusing for me. Okay, so this is added from the original slide actually. So if you see that from here, so the baseband bandwidth, this is bandwidth is equal to 190. This is actually supposed to be equal with the bit rate. So the baud rate is actually equal to the bit rate. Okay, so which is equal to 10 kilobit per second. Okay, where this bit rate, okay, is represented in terms of this parameter, the FM. Okay, the baseband bandwidth or the input frequency, FM, 10 kilohertz. Okay, so when you want to calculate the bandwidth, it is using the Carson's rule, 2 times delta F plus FM. Okay, so this is FM. So this is why is it like this? 2 times is okay. Okay, so this is the difference of frequency times 270 minus 100K. And then plus this one. So F maximum minus, okay. So you see that this one, okay. So this is F mark frequency minus F space frequency plus 2 times the bit rate, 2 times the FM, okay, the input. So that means this is mark frequency from the first oscillator, the high frequency, minus the space frequency, okay, from the second oscillator, plus with 2 times the FM in this example actually, where this is related to the 10K that we have found from the first part. So this is from here, from the baud rate. So we get 10 from the baud rate equal to 10 kilo. 10 kilo This is 10 kilohertz. We are not using bit per second. Okay, so the baud rate equal to the bit rate equal to the baseband frequency. So this is equal to 190 kilohertz. Okay, so the thing that confusing is this part. Okay, so this is actually related to the M. Okay, or in this case, for binary, it is equal to the baud rate and is also equal to the bit rate. For binary, this is only true for BFSK. When we move to high number of bit, this is would be different. Okay, so this is only for the binary. Okay, and this is the thing that happens in the receiver side. So where are we now? We are at the receiver side. Okay, at the receiver side, we want to demodulate the signal. Okay, so the first one, the picture above is for coherent. That means we are using the carrier signal, PCT, in the receiver to do the demodulation process. Okay, so that's why you see a carrier frequency over here, which is fed to the multiplier. So we have multiplier 1 and multiplier 2. Okay, so the input is FSK, the input. We have the power splitter, we split the difference in terms of power, and we put inside the multiplier. So we actually will split the frequency for FM and also for the FS space, the mark frequency and space frequency, which contain a different set of power. Okay, and put inside the multiplier, multiply with the carrier. Then when we multiply with two signal, we're going to produce low frequency and high frequency, right? As in chapter 3 that we have learned. Okay, we have the lower sideband and upper sideband when we multiply two signal in time domain. Then we use a low pass filter to select the low frequency. Select the low frequency, then we get only a single frequency output. Okay, then put inside the adder over here, which will produce 101010. Okay, so this part, okay, actually will convert positive and the will convert the voltage in terms of what we call power splitter. Okay, so we will produce the output 101010 in terms of logic numbers, data. Okay, the output is data. Okay, so for picture B, we are not using the carrier. Instead, we are using the BPF, band pass filter. Okay, so the band pass filter over here will select two different set of frequency. The first one will select the FS, and the other one will select the mark frequency. And then we do the demodulation using envelope detector. Then we produce an output, okay, a DC output where it will be converted into a data output in terms of 101010. Okay, so you might wonder, how does the receiver get the value 101010? Okay, so it depends on the threshold of the input signal into the system. So the receiver actually will compare with the threshold value. So if the voltage is less than the threshold, that means it will produce a logic 0 at the output. If the input to the system, okay, the input to the to this comparator the comparator will compare actually in terms of voltage. So if the DC voltage is less than threshold, less than the threshold, then it will produce logic 0 at the output. If the DC voltage is above the threshold, then we're going to produce a logic 1 at the output. Okay, so this logic number is based comparator based of the input voltage with the threshold value that is set in the receiver. Okay, so that's why even though we want to check whether this is a logic 1 or logic 0, so that's why we have to compare the output amplitudes in terms of voltage. So how big is the voltage? If the voltage is big, that means it produce the logic 1. If the input is has a low voltage, that means we're going to produce a logic 0 at the output. Okay, so the process is a bit complicated actually in the comparator, where we do the comparison with the threshold limit to determine whether this is logic 0 or this is logic 1. Okay, and this is it, and this will come out in the exam. So you see that for FSK, it is similar with the ASK that we have learned previously. Okay, where for the coherent FSK, the complementary error, the probability of bit error is 1/2 ERFC square root of EB over 2N0. Okay, so this is similar with the ASK that we have learned previously. Okay, and for the non-coherent, we are using the exponent function. Okay, 1/2 E power of EB over 2N0. So we can put a bracket like this. Okay, so this will come out in the exam, where you will be given a parameter of EB over N0, and you need to find how much would be the probability of bit error for the coherent detection. Okay, in the final exam, that means we're going to use this equation. This equation will be given in the question, okay, in the appendix of the question. Okay, remember, this will come out in the exam. Okay, EB over N0 will be given, and you need to find the probability of bit error. Find the PE. Okay. Okay, the last one will be the phase shift key, PSK. Class, can I get your response? Are you still there? Can you hear my voice? Can you see my screen?
Yes.
Yes,
Okay.
doctor.
Okay, thank you for the response. Okay, now is the PSK, phase shift keying. So phase shift keying is produced by changing the phase of the carrier in accordance with the input variation. Okay, so we normally write M PSK. Okay, so if the number of bit is equal to 1, that means we're going to produce two symbols. So this is binary, 1 bit. Okay, so that means it is 2 PSK, or known as PSK. It's just a terms, okay? Only the name, okay? The name given to this type of PSK. Okay, so we can have many types of PSK actually. So this is the most simple is BPSK. Okay, the phase of the output carrier shift between two angles that is separated between by 1 and by 0 and also by 180. That means for input logic 1 and input logic 0, the phase difference would be 180 degree. Okay, the phase difference of the carrier. Okay, when you change from 1 to 0 or 0 to 1 or 1 to 0. When the input change, okay, from 0 to 1 or 1 to 0, we're going to have a phase reversal for about 180 degree phase shift. Okay, phase shift. And this is the example of the generation of BPSK. Okay, so you see that the input binary data is logic 1, logic 0, logic 1, logic 0. Okay, so this is a unipolar. We put inside the level converter to convert from unipolar to bipolar. Okay, bipolar will change the 0 volt into negative. So we only have two polarity, positive and negatives. And this is a non-return to 0 in this example. Okay, then we put inside the balance modulator. So balance modulator, we will modulate with the analog carrier. Okay, we will modulate with analog carrier. Okay, so we're going to multiply the signal with uh, sine omega ct. Okay, so remember now your input, our input is either positive, let's say positive voltage, and also negative voltage. Let's say we choose the 1 volt, let's say. So either positive 1 or negative 1. Okay. So in this example, positive, uh, positive is represented by positive voltage is represented by positive 1, negative voltage is represented by negative 1. So you put inside the balance modulator. Balance modulator will do the process of multiplication in time domain. That means either you multiply with a positive 1 with sine omega ct, or you multiply negative 1 with sine uh, omega ct. Okay, so that means our output can have two possibility. Okay, two possibility. Either we have positive sine omega ct at the output, or negative sine omega ct at the output. Only two possibility. Okay, that means for sine, okay, for sine, the graph would looks like this. This is sine omega ct, and the other one is negative sine. So this is negative sine omega ct. Okay, so you see that the phase reversal is 180 degree between sine and negative sine. Okay, sine and negative sine, the difference gonna be 180 degree. Okay, and then band pass filter to remove the unwanted frequencies, then we transmit. Okay, so we transmit only these two possibility, either positive sign or negative sign for the BPSK signal. Okay, and then what? So this is, sorry, this is at the transmitter class. This is gonna be at the transmitter side. Okay, so we transmit either sign, positive sign, or negative sign. Okay, then at the receiver, so this is at the receiver. Okay, this is at the receiver. So we either receive positive sign or negative sign. Okay, and we have to produce the output. Okay, So that's why you see that the input here either positive or negative sign. And then put inside the bandpass filter to remove the unwanted frequency. Then we put inside the balance modulator. So this is a coherent detection where we use the carrier. Okay, we put inside the carrier signal into the balance modulator where it will do the multiplication process. Okay, so that means either the output is either sine multiplied with sine, okay, sine and sine, or positive, this is positive sine and sine, or negative sine and another sine. Okay, so both of these, sine and sine, remember in chapter 3, produce a two polarity output, right? Just a matter of difference in terms of positive and negative. Okay, so the output of balance modulator either positive sine and sine or negative sine and sine. Because our input is either positive or negative, we multiply with sine. So either the output is sine and sine, positive, or negative sine and sine. Low pass filter will select the low frequency output. Okay, we will select the low frequency in this example. Then we put inside the level converter. Okay, level converter will compare. Okay, will convert, will compare, okay, whether this is a logic 1 or logic 0 at the output. Logic 1, logic 0, logic 1, logic 0. So level converter will determine based on the level of the input here. Okay, if the input level is below the threshold, then it is supposed to be logic 0 at the output, or above threshold gonna be logic 1. So the converter will compare the input in terms of voltage and produce the output in terms of logic numbers, data. Okay. So previously we have asked this kind of question in the final exam where we give the input, positive sign or negative sign, produce the output. Okay. So in order to understand this, we can do the example. Let's do the example, the first example over here. Let's say this is the at the receiver. Okay, so we are now at the receiver. Okay, we are now at the receiver. So imagine that we receive sine. Okay, sine, positive sine from the input. Okay, so we know that if positive, that means it is supposed to be logic 1. How do I know that? So we have to go back to the transmitter. Okay, so positive sign is from the logic 1. Okay, positive sign is from the logic 1. Oh, I haven't explained here. Okay, so positive sign, you see that positive sign, this is actually logic 1. Negative sign comes from logic 0. Okay, based on this level converter, based on this level converter. So logic 1 is for positive sign, logic 0 is negative sign. Okay, so we transmit this into the medium. Okay, so positive sign, we know that this is actually logic 1 actually. So the output of balance modulator is, so positive sign input multiplied with the oscillator frequency, so it becomes sine square positive. Okay, if you see from the previous picture, this is a sine and sine, positive sine square. Okay, sine and sine or positive sine square. So according to trigonometry identity, we're gonna produce like this. Okay, 1/2, 1 minus cos omega ct. Okay, that means we have a high frequency, this one a high frequency signal, and this is a DC value. Okay, so you see that the output of the balance modulator is this one, 1 over 2, 1 minus cos omega 2 omega ct, where this is actually like this. Okay. So this is the output of balance modulator. Then if you see, we put inside the low pass filter. Low pass filter will select the low frequency signal and remove the high frequency signal. Okay. So when we put inside the low pass filter will filter out this part. It will filter out this part, and it will maintain this DC voltage, 1 over 2 of DC voltage. So this positive 1 over 2 of DC voltage produce logic 1. Okay, so it's true actually. So originally we assume that this is a logic 1. So we know that, oh, this is a logic 1 because we receive positive sign. And the output that we produce is also logic 1. So correct. Okay. And the second part, imagine if we receive negative sign. Okay. So negative sign, if we use in the transmitter, it is actually represented as negative sign, logic 0. Okay, logic 0. That means we are actually transmitting logic 0 from the transmitter. Okay, so the output, if you see the output here, negative sign from the input, we multiplied with the oscillator signal, the carrier from the oscillator. So we get negative sign square, sign and sign, negative sign and negative sign. So negative sign and sign, so we get sign square. According to trigonometry identity, negative sine square is equal to negative 1 over 2, 1 minus cos 2 omega ct. Okay, so this is negative 1 over 2 DC voltage plus 1 over 2 cos omega ct. Then we put inside the low pass filter. Low pass filter will remove the high frequency component. How do I know it is a high frequency? Because of this part. Okay, this part is actually 2 times omega c is 2 pi f. So this is 2 pi f c. So it is a high frequency output compared to this DC voltage. Okay, so finally we get negative 1 over 2 of DC voltage. So negative 1 over 2 is representing by logic 0. Okay, because it is a negative. So it is considered as below the threshold limit. So it will produce the logic 0. Okay, so the output gonna be either 1 or 0 or 1 or 0 and so on. Okay, next would be the uh, truth table. Okay, class, I think we're gonna take a break for 5 minutes. Can I get your response? Are you still there?
Yes.
Okay, so I'm gonna take a break for 5 minutes. I will resume again at 1:40. Okay, so let's take a break for 5 minutes first. Okay, so I will continue again. Can I get your response? Are you still there?
Yes.
Yes, Doctor.
Okay. So I will proceed with the next part is we are still in the BPSK. BPSK. Now we are looking the three things about the truth table, the phasor diagram, and the constellation diagram. Okay, so the first one is a truth table. So truth table shows the input and output. Okay, for input logic 0, the output gonna be 180-degree. Input logic 1, the output gonna be 0-degree. Okay, so this is the truth table showing the input and output. Then we have the phasor diagram, or we call it as the arrow diagram. Okay, so arrow diagram looks a picture B, like picture B, where it is actually consists of axis like this. So it is actually the above part is this is like a quadrant diagram. Quadrant diagram where this is for from 0, 90-degree, 180-degree, and then this is 270 and the last one will be 360. Okay, and this is also shown in terms of sine and cos. So the x-axis is representing as sine. Okay, sine omega ct. The left one is negative sine. Okay, negative sine omega ct. So the y-axis also produce a positive cos and negative cos. The above one is positive cos omega ct, and the one below is negative cos omega ct. Okay, so for the uh, input logic 1, it will produce 0-degree output. Okay, so you see that for input logic 1, it will produce a 0-degree output. Okay, 0-degree output. And input logic 0 will produce 180-degree of output. So that's why we have this arrow that pointing to the right and left. Okay, so you see that for logic 1, our transmitted signal is actually positive sine, as we have learned previously. And for input logic 0 is negative sine. Okay, then the third picture would be the phasor diagram. So phasor diagram, if you see from here, it is a dot diagram where it shows the location of the symbol. Okay, so the first one is for logic 1. If you see logic 1 is located at 0-degree. Okay, located at 0-degree. And that's why we make a dot like this at 0-degree for logic 1. Okay, and for logic 0, so we get the output going to be at 180-degree. Okay, 180 degrees. So you see that we have only two symbols. Okay, because this is a PSK where M equal to 2. Okay, so that's why we have two dot. Okay, so the number of dot here is representing the value of M. Now I have two dot, that means I have two symbol, that means the value of M is equal to 2. Okay, so what's the purpose of this actually? So actually we want to see how far does each symbol separated. Okay, how far does each symbol are separated? So imagine if you have many symbols. For example, if M equal to 256, so you have many dot. You have many dot. Okay. The closer the dot, the higher would be the chances of error. Okay, so this is also related when we want to find out how much would be the error. Okay, so the more the dot, the higher will be the probability of error. Okay, and this is the output of BPSK. Okay, so for input logic 1, logic 0, 1, 0, 1, 0. So we have the output. Remember, for input logic 1, we are transmitting sine signal, positive sign. Input logic 0, we produce negative sign. Okay, negative sign. Input logic 1, positive sign. Logic 0, negative sign, and so on. Okay, so the thing that you want to see here is actually the phase difference. So the phase difference from one point to another, from, you see that at this point, it happens a phase reversal for about 180 degree. The difference is 180 degree. Similar with this part, the difference is 180 degree. Okay, 180 degree, 180 degree. The difference. Once you change the input from 0 to 1 or 1 to 0, it will produce a phase shift for about 180 degree. Okay. So this is important for the final exam, okay, where you will be asked to describe about the BPSK. One of the potential answer would be to discuss about this graph. Okay, so this will come out in the exam. Okay. Next, this is about the graph, the waveform. So we have the input, we have the output, as we have learned. And over here, you see that the bandwidth is similar with ASK, where the bandwidth is 2 times the fundamental input frequency. Okay, so we get 2 times NFM. So maybe I can write like this, 2 times NFM. Okay, so if we have up to fifth harmonics, that means we're going to have 10 FM. Okay, and the probability of bit error for PSK. Okay, so this is for coherent PSK, and this is now we are at the receiver side. The receiver. Okay, so the probability of the bit error is equal to 1 over 2 ERFC square root of EB over N0. So you see that there's a slight difference compared to ASK and FSK. Okay, where there's no 1 over 2 in the bracket. Okay, tidak ada 1/2 dalam bracket. Okay, and for the non-coherent, it is 1 over 2 E exponent power of negative EB over N0, where you see that this also there's no 1 over 2 in the bracket, as in the ASK and FSK. Okay, so for your information, this will come out in the exam. Okay, where you need to find the value of probability of error by comparing with the FSK. So this will come up. So that means you have to calculate probability of error for FSK and also the PSK in the final exam. Okay, remember this is important. Only slightly different, okay, in terms of equations. Okay. QAM. So the last one will be the QAM. QAM is actually quadrature amplitude modulation, where it combines the ASK and also the PSK. Okay, combine ASK and PSK, we're going to produce a QAM. Okay, so QAM is considered as high modulation technique. Okay, which is used in the recent communication system, for example, 4G, 5G. So they are using the QAM modulation techniques. Okay, so you see that we have many types of QAM. Again, it is MQAM. Okay, so we're gonna see 8 QAM and 16 QAM. That means we are using 3-bit. Okay, 2 power of 3 gonna be 8. So that means 8 QAM is using 3-bit. Okay, so the block diagram is a bit complicated like this. Okay, you see that the input, we have 3-bit input is separated by QIC bit. QIC bit, quadrature, in phase, and control bit. Q for quadrature, I for in phase, C for control bit. So we separate the bits. One goes to the I channel, I bit go to the I channel, Q bit goes to the Q channel. Okay, so the level converter will change the input. Okay, either from 0, 0. Sorry. So the control bit also will go to the first level converter, and the other one will go to the second level converter. So now we have 2 input to the level converter. Okay, 2 input bit. Okay, so that means the level converter can receive in the table, if you see from the table, either 0, 0, 0, 1, 1, 0, or 1, 1. Okay, so this variation of input will produce a different set of output. Okay, different set of output levels. Okay, as stated in the table, we have 4 different set of level for each of the output of the level converter. Okay, similar with the level converter below, and we're going to produce a palm signal, pulse amplitude modulation signal, where it differs in terms of amplitude. Then we put inside the product modulator. Product modulator will do the multiplication process. Okay, in time domain, it will multiply with the sine function. Okay, if you see from here, sine function, and then we have the phase shifter. Phase shift of sine, we're gonna get cosine. Okay, and when we multiply these things, so we're gonna get the above part gonna be x sine omega ct. X can be any value. Okay, based on this output. And the product modulator below, okay, we're gonna get y cos omega ct. Okay, so linear summer, okay, will combine both of it. Okay, so we're gonna do x sine omega ct plus y cos omega ct. Okay, then band pass filter, then we can produce the output. Okay, so this is the output at the transmitter. Okay, so x sine plus y cos, okay, is actually can be represented as z of sine, okay, theta minus a, for example. Okay, so this one you can see from this example. Okay, so maybe I can just show the first one. So imagine that we have the input I channel and Q channel is 0, 0. Okay, so Q is 0, I channel is 0, C channel is 0. So the input now is 0, 0, 0. So according to the table, 0, 0 will produce output of the level converter negative 0.541. And then you multiply it with sine for the first level converter number 1. And for the Q channel, we multiplied with cos. So this is level converter number 2. Then we put inside the linear summer. Okay, we sum up both of it. Okay, so from this negative 0.541 cos minus minus 0.541 sine. Okay, if you see from the quadrant graph, okay, so this is located at, this is sine, this is negative sine, this is cos, and this is negative cos. Okay, for negative sine and negative cos, it is located somewhere. Okay, it is located somewhere on the third quadrant. Okay, somewhere in the third quadrant. So what we need to determine is the amplitude and also the angle. The amplitude is determined by quadratic summation, square root of 0.541 square plus 0.541 square, and then we get 0.765 volt. So the amplitude here, this one is this one, so maybe I can use a different color. This is 0.765 for the amplitude. Okay, and what about the angle? The angle is arctangent, okay, tangent minus 1 of 0.541 divided with 0.541, and then you're gonna get 45 degree. Okay, so 45 degree is actually this part, but if you want to find out how much would be the angle from x-axis, okay, it is actually 180 plus 45, so this is negative 135 degree. Okay, negative 135 degree. So the output of the linear summer is actually 0.765 sine omega ct minus 135 degree. Okay, so this is the first input of the QAM will produce this output. Okay, and you can follow for the next input 001, input 010, and input 011. So this is for 001, this is 010, and this is 011 input. Okay, for input. And you see what is the output. Okay, so this is the output, this is the output, and this is the output. Okay, and if you see the phasor diagram, you see that the first one is this one for the input logic 000. Okay, input logic 001, input logic 010, and input logic 011. This is for the phasor diagram, and we can get this value for the constellation diagram. The truth table is explained over here. So previously we get the first input 0.765 for the amplitude, and the phase is negative 135 degree. So you see that QAM determine the amplitude of the output and also the phase of the output. Two things. So that's why the name is QAM. Okay. Similar with 16 QAM, you're gonna get like this. So you see that 16 QAM, we have 16 symbol. Okay, so these are more prone to the error, but the good thing is we can get high speed of transmission. Okay, so I think that's all for chapter 4. So I will take your attendance, and then you can go anywhere you like. Okay, class. So I'm sorry for the delay. So now it's 2 o'clock. I'm sorry for taking more than required time for you. We are supposed to finish completely by 2 p.m., but I want to finish everything. So that's why we take until 2 o'clock. So you can open your QR code scanner. Okay, QR code scanner. Okay, so you can scan and you can go anywhere you like. Okay. See you again next week. And don't forget to submit your second progress report through the author. Okay, I have put in the author the submission in the group activities. In the group activities, you can submit the second progress report. Okay. So the due date in the author is until Saturday. Okay. So you have enough time. And if you need more time, you can inform me. I will delay. I will postpone the time a bit longer, maybe a few days after Saturday, so that you can write a proper report. Okay. So see you again next week.
Thank you, Doctor.
Okay. Welcome. Okay. Welcome.
Thank you, sir.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Thank you, Doctor.
Okay. Welcome.
Terima kasih, Doktor.
Thank you, Doctor.
Doktor, saya tak boleh scan.
Nama siapa?
Dania Najwa. Nur Dania Najwa.
Diana Najwa. Okay.
Thank you, Doktor.
Doktor, saya pun dapat scan.
Siapa nama?
Fitri Alif.
Fitri Alif. Okay, done.
Okay, thank you, Doktor.
Okay, welcome. Any more? Nur Aina ada? Dengan Angela Go? Angelina Go? Ada tak? So, Nur Aina, Ana Mardia ada ni. So, Aina, saya akan take you punya attendance. Aina. Aina Mardia ada. Angelina Go tak ada pula. Okay. So, I think that's all. So, see you again next time. Stop presenting.
Thank you, Doctor.
Okay.